Welcome to this IUN Community Garden Session, Soil, It's Alive. The presenter for this session is Victoria Jostes. In her capacity as a master gardener, Victoria has revealed her passion for the natural world in self-authored presentations to civic groups, gardening clubs, and schools across Northwest Indiana. Being a master naturalist and amateur photographer rounds out her abilities to bring nature indoors to adults and children alike, stirring imaginations as well as awareness. Welcome, Victoria. Thank you for being here.
Thank you, Leslie. I really appreciate you folks having me. I enjoy doing this for you. Okay, let's begin. Greetings, everyone, and a warm welcome to you all. I'm really excited that you're here to see our presentation called Soil, It's Alive. I've been thinking a lot lately about my master gardener education and the educator in particular. He was a very learned man, lots of experience. And among the pearls of wisdom that he shared, one, ironically, stands out vividly. Stan Sims assured us that soil is never referred to as dirt. His point was dirt is why we sweep the floor or wash the car or bathe the dog or 100 other examples. But we're going to stay in that same vein today. We're going to dig deep and we're going to get the real scoop on soil. And at the same time, maybe we can answer a few burning questions like, has the soil that I garden in today been around forever? Is all soil alike? What's soil made out of anyway? Yes, soil is amazing. And for a number of reasons. Did you know that soil cleans the air that we breathe? It captures the CO2 that we're not supposed to release into the atmosphere, and it holds on to it, thereby having influence over climate change. And that's in our forefront every day from now on. It also cleans our water. We know about wetlands, how the soil and the plants in wetlands clean the water that comes into it, so that when that water leaves the wetland, it's much cleaner than it went in. Now, here's something really important about that. Wetlands also have a direct connection to groundwater. So when that water seeps out of the wetland and gravity pulls it down, it finds the groundwater and actually recharges it. That's terribly important for us in our state of Indiana, because 70% of our residents depend on that groundwater for drinking. Many, many gifts are given to us from soil. We wouldn't have the homes we live in with the structure that's made of wood. We wouldn't even have a chair to sit on. We wouldn't have your Levi's 401s without soil. So we need to remember that soil, although it's considered a renewable resource, I guess it really is if you have 100 or 200 years to wait for an inch or two. This useful cutaway diagram shows us the four layers or horizons of soil. Let's look at the most important one down here at the bottom. It's called bedrock. We understand that bedrock forms the Earth's crust, solid rock. And the legend on the cutaway says that bedrock is the lowest layer of soil. How can that be? Let's think about this. When we travel this beautiful country of ours, we're very liable to see some extraordinary natural wonders. The first that comes to my mind is the Grand Canyon. The majesty of it. It blows my socks off. And then there's the Rockies. The first time I saw the Rockies, I had tears. And then we have perhaps the Smokies, older mountains that are kind of rounded at the top. If you've ever had the great good fortune to visit Hawaii on the Big Island, perhaps you have been able to witness the eruption of Kilauea. Now, all these wonders are obviously very different. Think about how they really look. They're different colors, they're different textures, they're different forms. It's because of what they're made of. They're made of that bedrock that is our Earth's crust. What we see has been forced to the surface of the Earth. The reason it looks different, and it is different, is because bedrock is made of minerals. Different minerals in different places. That's what makes these features look different. And it stands to reason, if the legend on our cutaway is true, that bedrock is the lowest layer of soil, that it is the building block of soil. That means that any soil formed from that particular bedrock is going to be different in different regions. We've got that settled. Now, here in this Midwestern part of the country where we live, we don't seem to have those mountains and valleys and canyons, but we had something else. We had the great glaciers. They would advance and recede, and advance again and recede. They were so huge, so monumentally big, that they were heavy. Ice, solid ice, weighing on the surface. And as the glacier advanced and retreated, it tended to grind up anything beneath it. So as it receded, it left glacial till. Almost encircling Lake Michigan is a ridge called the Valparaiso Moraine, all made of glacial till. If you've ever visited Gabus Arboretum at Purdue Northwest, you will have stood on the continental divide of that Valparaiso Moraine. So glacial till is a gift that was given to us from glaciers. As the glaciers moved in their awesome size and weight, they were able to level mountains, fill valleys, and create great lakes. They gave us a leg up on the creation of soil. That soil has made us the breadbasket of America. We don't have mountains, we don't have canyons, but we have exquisite, exquisite soil. We said that soil is different, the rocks that it comes from is different. As many different types of rock as there are only three main types. And under those three main types, a number of subtypes. The first main type is igneous rock. This is what it looks like. It's black. It's one of the many subtypes of igneous rock. We're calling it obsidian. It's black. It looks like black glass, volcanic glass. It was ejected from a volcano and it cooled so quickly that there was no time for it to crystallize, hence its smoothness. Many, many eons ago, our early indigenous discovered that obsidian could be chipped or knapped in the same way that they chipped or knapped flint to create projectile points and tools. And where did they get this obsidian in the United States? They found it at Obsidian Cliff. Even though the area had 45 other places where they could have obtained it, they chose that stone that was produced near Obsidian Cliff because of the quality of it. It was the best in the area. If the tribes that used obsidian did not live in that area, and who wouldn't want to live in the area? The Native Americans had everything they could possibly need there. They had an abundance of game and anything they could possibly use in their lifestyles. If they didn't live in the area, they would make annual pilgrimages, or even more often if they had to obtain this useful stone that was a major part of their existence. So they came to the area, they found Obsidian Cliff, and they started to pick up the rocks that suited their purposes, the sizes that they just needed, because we know they wasted nothing. And no, they didn't have to climb the cliff to get the obsidian. There were deposits of it in the area that were really easy for them to get to. And so they used this area because of the quality of the rock and the ease of obtaining it. Oh, I guess I didn't tell you. Obsidian Cliff is in an area that we now call Yellowstone National Park. The second type of rock is metamorphic. Here's an example. This is a folded, foliated, metamorphic rock. Foliated means it has layers. The layers were formed by elongating the crystals within the rock. This one is folded. How do you fold a rock? Very slowly, with heat and much time and pressure. We can see the layers are going up in this direction. They make a U-turn and come back. We can see that it truly is folded. This white rock is unfoliated because its crystals refuse to be elongated. Perhaps that's why the great sculptors chose marble to work with. This last example is called mica schist. It's a combination of those two rocks. In this case, the mica is the white spots on the rock. The red crystals, and there seem to be quite a few of them, the red crystals are garnet. Yes, garnet, gemstones, my birthstone. When you find garnet in a rock, you can be sure, I'm going to try and make this show for you. You can be sure that the rock is metamorphic. This is a garnet that was mined for me on BLM land, Bureau of Land Management in Nevada. The Bureau allows folks to come in and actually mine for garnet stones. And if you noticed on that was that stone that I just held up, the rhyolite rock was mined to look like the letter V in my name. Metamorphic rock is formed in a very different way. A metamorphic rock doesn't start out as metamorphic. It starts out as a different type of rock. And then with heat, pressure, and time, it flip-flops, and then it's metamorphic. The last type, major type of rock is sedimentary rock. Here's a short list of some of the subtypes. Conglomerate rock looks like this. It looks like Rocky Road fudge. It's got chunks and bits and pieces of other rock within the sediment. And we know what sediment is. It's material that falls to the bottom of a body of water. Imagine we're in the ocean, a very deep part of the ocean. We know how heavy water is. All of this material falls to the bottom. It can be organic, it can be inorganic, it can be once living marine creatures or their skeletons or shells. It continues to fall to the bottom. The great weight of that ocean water creates tremendous pressure on that sediment. With much time, that pressure creates sedimentary rock. 73% of the Earth's surface is covered by sedimentary rock. Think of the relationship of the amounts of ocean compared to landmass, and you can see why 73% of the Earth is covered with sedimentary rock. There are biochemical rocks in the sedimentaries. One is limestone. That's made again of skeletal remains and shells of various organisms. And under heat, pressure, with a lot of time, limestone is created. The same process happens with coal, although it's made of something entirely different. It's made of ancient plant materials. It's hard to believe that something as solid, pardon me, as coal is made from plants. But again, under those same conditions, heat, tremendous pressure, and a lot of time will get you coal. Perhaps because it's made of plants, perhaps that's why we call it fossil fuel. Shale, black shale, can contain petroleum. Other shales can be a cap or a container for subterranean deposits of natural gas and petroleum. Oh, let me go back. Down here, this pretty clear, beautiful crystal. Next winter, when you're in the Ace Hardware and you are looking for something to melt the ice on your front porch steps or on your sidewalk, do not pick the bag that is labeled halite, that's salt, and you don't want to damage your concrete or your landscape. We're coming back to our cutaway, and now the bedrock has been broken into big chunks. Pieces of it have been created, and it has become parent material. The legend says mostly rock that has been slightly weathered. That's what parent material is. It also says that there aren't many things living down there. I didn't think anything lived that deep in the earth. Parent material. It needs to be weathered. And let's figure out how it gets weathered. Processes involving water, erosion, temperature, time, plants, individually those, or perhaps in combination. This slide has examples of physical weathering. We'll look at the Grand Canyon. We understand that the canyon was formed by a river, the Colorado River, over many, many years. It took eons to form that canyon. Here is a rocky outcropping that has been heaved up to the surface of the earth. And we learn from this outcropping that bedrock is laced with tiny pores and tiny cracks invisible to the naked eye. But water can find those openings, and it does enter. When winter comes, the water freezes. We understand that when water freezes, it expands. Therefore, those cracks and pores are forced to be a tiny bit bigger. And this happens every year over time. The cracks are no longer invisible. In fact, they're getting bigger. They become big crevices. Here comes the wind. The wind blows in organic matter, inorganic matter, as does the rain. The rain deposits those things in the crevice. Seeds are blown in there as well. The birdies drop seeds in the crevice. The seeds germinate, send out their leaves, and they send down their roots into the bottom of that crevice, and it does its own form of weathering, increasing the size of the crevice. Soon that crevice is so big that it will no longer support this big chunk of rock, and gravity calls to it, and it tumbles down the outcropping, chipping off more rocks, both from the piece that's falling and also from the outcropping, creating smaller stones. Physical weathering. Notice the scars on this rock. The rock evidently is softer than that top outcropping. It's a different kind of rock, has different ingredients that make it softer. What's scarring it, and you can see there are holes in it, many scars. What's causing that is acid rain. It's further weakening that soft rock. This section here became very weak to the point where a good windstorm actually blew out that whole section in one big piece. And it will continue to crumble under the effects of weathering. This last example is a boulder, a huge boulder that has been battered by waves for years. And you can see how the water and salt in the water has changed that rock and worn it away. It has even formed these huge tunnels. The salt has done this. These holes are called trophoni. They actually have a name. The particles that have been worn away from the big boulder have landed in the ocean. You can see by the color of it, there is a tremendous amount of sediment there. I don't know that that water in that particular area is deep enough and heavy enough to cause cementation by its weight. But that is a prime example of water and weathering. Chemicals can cause weathering. When you combine carbon dioxide, that CO2 that we're not supposed to release into the atmosphere, that miraculously somehow is getting there anyway. When you combine that CO2 with H2O, water, you get carbonic acid. It's a weak solution of carbonic acid, and it has been known to do a number on rocks. It can weather rocks. When that rain falls with CO2 in it, and it has formed carbonic acid, by the way, that same carbonic acid is what you feel tingling in the bubbles on your tongue when you drink your soda pop. Yes, there's carbonic acid in your soda. When that weak form of carbonic acid settles into the earth, gravity pulls it on down, it can pick up even more CO2. And the rubber meets the road when it encounters limestone. Limestone is very susceptible to dissolution by carbonic acid. If you've ever been to Mammoth Cave, you've seen sites like this, where the carbonic acid dripping into the rock forms enormous caverns and passageways. And just because those structures have been formed, that doesn't mean the dripping stops. It keeps on going. And we see stalactites and stalagmites have been formed. There's a pool of it on the floor that keeps doing its disintegration work. Eventually, the stalactites and the stalagmites can meet and form columns. We just spoke of acid rain. Here's another example of exactly what can happen to stone. Not only stone in nature, but the stone that man has used to create buildings, giant cathedrals in Europe that are hundreds of years old, sculptures, statuary, and all of this is being worn away. The statues look like they're behind a veil because the features aren't as sharp as they used to be. Historically speaking, the materials that produce acid rain were provided through the action of decaying vegetation when nitrogen could be released, and it would combine with water and form nitric acid. After volcanic eruptions, there was a certain amount of sulfur in the air that the rain picked up and fell as sulfuric acid, a mild form. acid rain doesn't necessarily have to be precipitated in rain. It can be acid snow. It can be acid fog. Think about that things are covered from the top, from the bottom, from the sides. Things are engulfed in fog. And it can also fall as particles of a solid. Who ever thought of oxidation being a form of chemical weathering? Here's an example of a rock that's filled with iron oxide. Here we have iron, here we have oxygen. When they meet, we have iron oxide or rust. You can tell by the color, rust. That's what's in these natural structures, these cone-shaped structures in nature. I have to admit, I don't know where this photo was taken. It illustrated my purposes quite well, but I'm not sure exactly where it was. It could be in our Southwest, although I've never seen structures quite like this in that area. But look at the vegetation here. Look at the vegetation. And when you think about these cone-shaped structures and how the stones that are filled with iron oxide become crumbly and they tumble down the side of the structure, taking other stones with it and breaking them all into small bits, even into dust. The dust falls to the ground, the wind picks it up and disperses it. Look again at these green plants. I'll tell you what they remind me of. They remind me of the time that I accidentally dumped a part of a bag of ironite on my lawn, and that section of lawn was blue-green for quite a while. If this was indeed in our Southwest, and these bush-type plants could indeed be sagebrush. Think about this. The sagebrush color is normally a pale gray-green. These are not gray-green. I think they are getting over-fertilized from the iron oxide in that rock. We talked about plants germinating in a crevice on that rock formation in an earlier slide. They took root, they germinated and took root in baby soil inside that crevice. That's what's going on in this rock here. The plant is growing, not only sending its roots to the bottom to enlarge the crack at the bottom to accommodate more soil. The soil is being held in place by the plant. When the plant dies off, its dead vegetation will be contributed to the soil as organic matter. Its seeds will also land in the soil to continue that annual process of weathering by that little plant. This other illustration shows a rock, and on the rock we see moss and lichen. If you were to scrape off all that vegetation and scrub that rock really well, you would see that the rock is terribly pitted. It's being weathered by those plants. And how can that be? A rock is a very hard substance, yet it's all pitted. It's because those plants emit a certain amount of acid that's strong enough to pit those plants, and it also makes it strong enough to allow them to obtain just a tiny particle now and then of nutrition from the rock in the form of minerals. The rest it gets from the atmosphere. This is the last bit of weathering that we're going to look at: erosion. Without erosion, weathering would take even longer than it does. And we saw in the slide about iron oxide, we saw how the wind took the dust that was created by weathering and it dispersed it. That's erosion's job. Here's the definition of erosion: the removal of surface material from the Earth's crust, primarily rock debris created by weathering, transporting these materials by wind, water, gravity and scoured by ice. That makes everything that we just spoke of fall into place. This is an oxbow that's out in our western states. And it was formed by the action of the water in the river behind it. The river comes down here and makes a snappy turn to the left. But since it wore down the rocks behind this center post, it wore those rocks down, it emitted the water from the river and created the oxbow. It wore down, you can see where it wore down that rock, it weathered it down to form the oxbow. And what happened to the particles that were worn down? It was carried away in the water. You can see how it was deposited around this center post. And here's a sandbar made of it, back going around the back of it. Who knows, in another 1,000 or 2,000 years, maybe that silt will build up and eventually block off the river's admittance to that oxbow. But it, as I said, in another 1,000 or 2,000 years. If you've ever attended one of my presentations in the past, you will know that occasionally I'm apt to take a detour. Today, we're going to do that. It's time. Have you ever wondered how gemstones are created? I began to think about that as I was researching this presentation, and this is what I came up with, that gemstones are formed deep within the earth. We see the bedrock here. We know that's the earth's crust. Under that is the mantle, molten rock. And you remember from middle school science, all about convection currents, that when you heat a liquid, it tends to rise, and as it cools, it falls again, it's heated, and it rises again, and this convection current is formed. That's what's going on in the mantle to a great degree, because the heat there is intense. And the currents can produce some violent activity. Sometimes it cracks off chunks from the bottom of the bedrock, and they tend to fall into the mantle. Some of them stay in the mantle and melt. Others are tossed back by that convection activity, and they can actually chip holes into the earth's crust, into that bedrock. And sooner than not, steam enters those voids. What's carried in the steam are crystals. The steam comes from liquid, from fluids, actual fluids within the mantle. So the steam can carry mineral crystals with it. Because the bedrock is cooler than the mantle, the steam condenses, leaving the crystals clinging to the walls of the void. If conditions are right, those crystals can grow. What are the conditions? Heat, pressure, time, and space. Space for the crystals to grow. And they do grow as long as the conditions are favorable. But conditions can change. They can even stop or even pause and then resume. When they stop and then start again, perhaps it's a new cloud of steam with different crystals, because the conditions are different. A different gemstone from different crystals will grow. Over much time, with all those conditions, gemstones are created. Then it happens, the tectonic plates that float on the top of that mantle become very active, and they can crash into each other with, with great force. And when that happens, sometimes upheavals happen, where big sections of the crust, the bedrock, is pushed to the surface, where we can see them. If we were there thousands of years ago, we would have seen these gemstones exposed. However, weathering happened, It was doing a number on the rock and also on the area where the gemstones were. The wind blew and the rains came and deposited organic and inorganic materials and covered those gemstones. And just as they happened, the rain and wind returned. This time, they were weathering the rock. They also weathered the coverings on those gem deposits because they were only covered with soil. They weren't rock that had to be worn away. And the gems were exposed for our gratification. This rock happens to be a brown diamond. It's 3 carats, and it was found in a state park in Arkansas, where people are allowed to come in and search for diamonds. The same gentleman that found this brown diamond in 2011 found a 3-carat yellow diamond, and a few years later, a 6-carat white diamond. But make no mistake, these are not gem quality stones in that state park in Arkansas. They're probably industrial strength, but they're still saleable. And the fellow that found this brown diamond and the other big ones found 400 other stones, and he was able to sell them all. I'm going to show you just a few gemstones. These are made from quartz, macrocrystalline quartz. These crystals make transparent stones. I chose amethyst because I like it. Have you ever seen a geode with amethyst and quartz crystals in it? They're breathtaking. They're just beautiful. So now we know they're made from large crystal quartz. Here's purple amethyst. Citrine is yellow amethyst. Ametrine is the combination of the two that's found in nature. Prasiolite is a beautiful, soft green amethyst color. I love it. Smoky quartz. Rose quartz gets its color from titanium. And here is tiger's eye. Tiger's eye has an inclusion in it. In this case, it's in the form of asbestos, and that's what forms the tiger's eye. These stones are made from cryptocrystalline quartz that produce translucent or opaque gems like carnelian, opal, bloodstone, jasper, chalcedony. That's what generally fills up a thunder egg. This is cryptophase. I think that's how you pronounce it. It's like opal in that it's a very delicate stone. It's very fragile. You have to store it in a box, in a drawer, otherwise it will dry out and be ruined. This one is so soft that you can actually carve it. Here we have agate. Agate is formed in the same way that geodes and thunder eggs are formed as a gas bubble in the magma, and it floats up, and the outer shell of that sphere hardens, but it still has the pores and tiny cracks in it that admit water. The water has crystals in it, and they begin to grow. More water comes in, different crystals from different minerals, they begin to grow. And that's where the different colors come from inside agate. If you are making a geode that it's formed in the same way, they are most often filled with chalcedony. This last stone is onyx, and we have seen that in cameo carvings. This is my favorite. It's an opal. It's called moss opal because the inclusion in it resembles moss. We're almost there. We started out with bedrock, broke it into huge chunks. Then it became parent material and it was weathered. The bigger chunks became smaller chunks. Now we have matriculated to subsoil. Subsoil has 3 kinds of soil in it: sand, silt, and clay. It's predominantly clay. It's sticky, probably a little stinky. It is very difficult to manage. It is not uncommon in a brand new housing development for the developer to bring heavy equipment in and skim off the topsoil, leaving subsoil behind. The legend here says that this subsoil is not done yet. It's a long way from being done, actually. It's deficient in some superior ingredients that would make it topsoil. It has no organic matter. It has no air. Why does it need air? It needs air for plant roots. And it needs living organisms to finish it off entirely. Now, we're going to take another detour. We're going to go into your backyard, but you have to bring a jar with you, a straight-sided jar with the label off of it. It's got to be taken off, scrubbed off. You will also need one of your trowels, because we're going to take a scoop or two of your soil and put it into that jar. Before we put it into the jar, we're going to pick it over, just like you were picking beans before you boil them. You're going to pick over that soil and make sure there are no stones in it, nothing metallic like nuts or bolts, because after you put the soil in that jar half full, you're going to fill the rest of the jar within an inch of the top with water and put the lid on very tightly. If you didn't pick out the stones or anything metal in there, when we shake that jar up, your jar will crack, and you don't want that to happen. So shake the dickens out of that jar. Keep shaking it until all the lumps are gone, and all you have left is sediment floating around in that jar. Carefully set it down in a quiet place for 24 hours. After 24 hours, don't bump the jar, because some of those layers that form can be less than a quarter of an inch in thickness, and you don't want to bump it and ruin this night's work. Otherwise, you have to shake it and have it set again. You're going to see layers. The topmost layer in your jar is going to be clay. It'll be about this color. The middle layer is silt. That's about that color. And then you'll have a layer of sand on the bottom. That's how they always happen. Clay on top, silt, and then sand. So now we're going to find out what kind of soil you have in your yard. If your jar looks like the first one, if the clay layer is the whitest, it's the predominant soil within that jar, you have my sympathy and you have my soil. You have clay soil. Not easy. However, if your jar looks like the third jar, and the bottom layer, the sand layer, is predominant, same sympathy, different soil, you have sandy soil. However, if your jar looks mostly like the center jar, you have what everybody wants. You have silt soil or loamy soil. Loam is what everybody wants, and Martha Stewart probably has the only perfect soil around. She probably has wonderful loam and can grow anything in it at all. But this is not a soil test. This will give you an approximation of the kind of soil that you have in your yard, approximately, but it doesn't tell you the condition of your soil. It doesn't tell you about the minerals in your soil, about the organic matter, the pH, the cation exchange capacity. It doesn't tell you any of those things. And how do you get those things? How do you get to know what that is? You call your county extension agent and you request a soil test. We'll talk about that. This is a copy of the form from one of the companies that administers soil tests. This is the company that I used for my last test. This space here, you fill in with the name of your county extension agent, because when the result comes, some will go to that person and some will go to you. It's all the same stuff. You have the same information. But if you have any questions about it, that's who you can call. If there's something on there that you need clarification on, you have a person, a real person who can explain to you. So you fill in this top part, fill in the middle part. This is not complicated. The answers are supplied to you. All you have to do is pick. Are you going to grow flowers here? Are you going to grow trees here? Are you going to grow veggies here? That's all there is to that. Then you go to the bottom that has explicit, simple instructions of how to take a good sample. And you create the sample and you put it in the little bag that they send you. And you include your check. It's going to cost you a little bit of money, but you will see it is by far one of the best things you've ever bought. You can choose to have either a basic soil test or a more comprehensive one, a complete test. If this is your first test ever on your soil, I would choose the complete test. If you had one within the last couple of years, you can do the basic test and then repeat it every 3 years after that, so that you can see your progress. You see how long it takes to form soil in nature. It's not going to take us quite that long to fix your soil, but it does take time. So it's good to keep track of that time every few years by doing a new soil test. This is an example of what your soil test will look like. The tested minerals and conditions are listed on this side. I see organic matter here. I see cation exchange capacity. I see pH and all the major elements and the micronutrients also. They're in numeric form. They're also in graphic form. What's below that is the magic. It tells you what you're deficient in. It tells you what you have plenty of. It tells you if you're going to fertilize, this is what you use, this is when you use it, and this is how much to use. So you're not wasting your time out there, wasting your money, ruining your soil even more by putting the wrong thing in there. Some folks, if they have clay soil, think they should dump a bunch of sand in there and that will dry it up. It creates a very hard concrete-like mess. So this will be one of the best things that you have ever done for yourself. I spoke of cation exchange capacity, or CEC. It's really very easy to explain. In your soil, the clay part of it and the organic matter part of it is negatively charged. Think of your soil as a big battery. And then you have the minerals, the plant nutrition floating around loose, looking for something to complete themselves. They search, and all of a sudden they find the clay and the organic matter. And by George, they partner up. Negatives attract. The negatives partner up with the positives. Now that soil has the availability to give nutrients to the plants. The nutrients are available now. Those minerals were floating around loose. Those cations were just searching around loose. And the plants are starving because the nutrients are not available to them. As soon as they partner up with the clay and the organic matter, then the plant roots are fed with an exchange. Here come the positively charged cations feeding the roots, and the roots are exchanging back their hydrogen ions. Super simple, but very important. The next step in that is the pH. You've heard pH many times. pH is the measure of acidity or alkalinity in your soil. It's a graph. It starts at 0, very acid, ends at 14, very alkaline. Midway between is the neutral zone. Half of 14 is 7. 7 is the neutral zone. Here's a graphic to show us that this is the neutral zone at 7. What do these colors mean? They relate to this list of minerals. If the bar graph is red in your pH, say your pH is 8.5. If the bar graph is red, then no minerals are going to be exchanged. If it's yellow, some will be. If the bar is green, green means go. You can have the minerals. So if your pH is 8.5, that's pretty alkaline. We'll look down the graph. Nitrogen, it's almost all red. Phosphorus is red. Good. Potassium's green, sulfur's green. Calcium is red. You can get some magnesium, no iron, no manganese, a little boron, and no copper or zinc. All those minerals are necessary for a plant to function properly. Now, if your pH was 5.5, you can see by the colors what's available and what is not. However, in the neutral area, neutral pH, everything's available in its best form, with the exception of iron, and that's just a medium amount. A small amount of iron is really needed by your plants, but we know what chlorosis looks like. If a plant should happen to be a little on the light side with iron, we know what to do with that. So it is said that garden plants, with the exception of the acid-loving ones, the blueberries, the rhododendrons, the azaleas, those acid lovers are not in this group of garden plants that I'm going to mention. Just ordinary garden plants. It is said that they do the best in a neutral pH. And now we can see why. The availability of nutrients is there. Plant nutrition uptake in relation to soil pH. Soil pH governs how much food your plants can get. If the pH is right, that in itself will allow your plants to be fed. pH also governs cation exchange, how the minerals find their partner to make food available. If you don't have your soil tested, you cannot know what the pH is with accuracy and allow your plants to be the best that they can be. See, in all this time, you thought you didn't have a green thumb. A good pH level also increases the microbial activity and decomposition of organic matter. We'll talk about that right now. These little critters are what bring your soil to life. First of all, we have the microbes that break down organic matter initially. Then we have the bigger guys. In nature, we have the producers, the consumers, and the decomposers. These microbes are the decomposers. The rest of these guys are the consumers. They eat everything. They eat organic matter. They eat dead critters. They eat everything. And when they excrete the waste from that, that is excellent nutrition for the plants. They also exude a certain acid that will help to dissolve organic matter. Now I see a big old earthworm here. All of these insects, these invertebrates, are crawling around in your soil, aerating it, giving it airspace. This worm is a champ at creating space. He worms his way through the soil in a different way that the other insects do. As he's worming his way through, he's not just pushing the soil aside, he's eating his way through it and eating whatever is in his path. And when it passes through his digestive tract and it's excreted, we call it worm castings. Excellent, excellent nutrition for plants. Now, when we talk about these organisms within your soil, if we were to take from healthy soil an acre of 6 inches of topsoil off that acre, just take that whole acre of topsoil and pick out all the critters, they would weigh 1.5 tons. In one handful of healthy garden soil, if we took out all the critters and counted them, there would be more organisms from that single handful of soil than there are people on this earth. Needless to say, because these organisms are bringing soil to life, they play a vital role, not only in soil health, but our goal is to have plants that are healthy. So is the goal of these plants, of these organisms, to make plants healthy. That's why they exist here. We spoke of the microbes that include bacteria, protozoa, and fungi. This is another type of fungi. It's called mycorrhiza. It's a very special fungus. 80 to 95% of the plants on our earth partner up with mycorrhizae. It is a partnership that's beneficial to both the plant and the fungus. We call that a symbiotic relationship. Both parties benefit. You can see how the mycorrhizae have attached to the plant roots. Once they're attached to the plant roots, they reach out. They can reach out 200 times farther than those plant roots can go. And they're searching. And they bring back nutrition and water to the plant. They bring back things that that plant can never get by itself without mycorrhizae. That is one half of the symbiotic relationship. The plant is benefiting from the mycorrhizae. Now, if this is a true symbiotic relationship, the plant needs to give something back to the fungus. That, my friends, you will have to find out in your resource packet that you will receive from IU. I created a sheet there, and it's not a long one. It's just one sheet that explains the wonders of mycorrhizae and plants together. Remember, they're all over the world. Almost every plant uses them. Yes, you want them in your garden. Perhaps tilling, when you think of the network of mycorrhizae, the network of those hyphae that reach out, you'll think twice about using a tiller in your garden. We know that some farmers do no-till farming. They don't want to disturb the field that they're growing in. And part of that is that they don't want to disturb the mycorrhizae. One last thing about, about adding, pardon me, organic matter to your garden. It can be in the form of plant clippings, healthy plant clippings, no diseases, no insect pests on there. Yes, you can use brown twigs. We talk about brown and green when we're composting. You can use twigs from bushes or trees, small twigs, because it adds texture to your soil. But remember, big pieces take much longer to break down. So think twice about that. You can use compost, the kind that you make in your own yard with a compost pile, or the kind you buy in a bag, or pit composting, which is my absolute favorite. You dig a hole in your garden and you put in kitchen scraps, no dairy, no fat, and you put a shovel full of soil on top, and you keep building that until the hole is filled. Remember to cover it with like a garbage can lid and a big heavy rock, a block of some kind, so that the smart but nosy raccoons don't get in there and no dog goes after it to dig up to see what you've got. You can also use manure. Manure is excellent. I have used horse manure in my garden and got wonderful results. I use horse because it's convenient for me. I don't have access to cows. Manure, once it's aged, will not offend anyone. Just make sure you don't have the friend of yours that has 2 horses and a great big pile of aged manure. You don't allow that person to come and give you a whole truckload of manure and you put it on all at once. Bad idea. Soil takes a long time to build, and dumping an entire bunch of manure on it at once is a bad idea. Little by little, every year. I've even used fresh manure when in the winter time, when everybody's windows are closed, and I'm not going to offend everyone. And by spring, it's aged and you can turn it in and it's great stuff. If you've never used manure tea for your roses or other flowering plants, try it. You'll like it. There are great benefits from using organic matter every year in your soil. It provides food for living organisms. That we know. It increases aggregation and soil aeration. We'll talk about that next. It decreases the stickiness of clay. Hallelujah. And then we have the fact that it increases cation exchange capacity. Remember, we said the clay and the organic matter has a negative charge to partner up with the nutrition. This is in your packet as well. I'll briefly tell you that aggregation is illustrated here. You see the clumping of the soil. Here's the soil fragments. Here's organic matter. This is tiny little water droplets, and this enables everything to clump up. The water and the organic matter allow the soil to clump. So what? So it creates voids in between the clumps where oxygen can be, where water can drain through, water coming through, seeping through the earth, brings more nutrients. I'm going to let you read this bottom part for yourself when you go through your packet. Now we have finally arrived. It's complete topsoil. It has all its components. Everything is in place, and you can grow your petunias and your corn and your tomatoes with great joy. You'll have the best plants that you have ever had. On that note, I have one last thing to say. These soil tips are also in your packet. The first one talks about not working your soil too early in the spring. It's wet. It needs to dry out. A couple of weeks ago when we had all that rain, I swear it rained at least twice a day. And I wanted to go into my backyard and see what things were doing. And I took a step and I squished and I got back out immediately. When you work your soil too soon and you squish, you're not only compacting the soil, but you're also squeezing the air out of the soil. And we know that plant roots need oxygen. So resist the temptation to go out too early to work your soil. And I'll tell you what you can do while you're waiting. You can call your county agent, get a soil test kit, test your soil, send it off, get the result back, get all your ducks in a row. You need to know what you're going to do, what you're going to need for your soil. You got it all set up before you even can go out there and work it in the first part of May, because I think it's going to take a long time for us to dry out this year. Enjoy, in the meantime, the Proven Winners website, so you can know also what you're going to grow out there. So enjoy these tips. On that note, I will say to you, bon voyage and happy gardening. You got to love this guy. Before we have questions answered, I have to show you, this is a geode. It would have been a thunder egg, but it has a hole in it. That's the requisite for a geode. It's got to have a hole in it. And this geode, when it was cut in two, it revealed a mirror image of Cookie Monster. And I'll leave that thought with you. Leslie, do we have any questions today?
Thank you for the excellent presentation, Victoria. And we do have a question from a participant. The person asks, if you have an organic garden that you've prepared, would you recommend having a soil test done on that as well?
Sure. Everybody's got to have a cation exchange and a pH level to build on. Absolutely, you do. You can be deficient in some things or have an excess of some things and not even know it. And that soil test that you get back, that result, is peculiar to your yard only. We said that soil can be different in every location. Your next door neighbor, you would assume, has the same soil that you do. They have the same soil type, the general type, but it's not the same as yours. She has not done what you have done to your soil. The additives that you have used are going to be entirely different from what she has used. So your soils are different. The result that you get is custom to your soil and your soil alone. Yes, you should have a soil test.
Thank you for that answer, Victoria. We do have another question. Do mineral mines differ in the stones that they would bring up?
Remember, we said that all rocks in all locations can be different depending on the mineral makeup. So the stones that are found in a mine are different from the kinds that you will find in another location. Different stones are found in different places because the minerals are different. And some of them are found in veins and some are found singly. When you look at gold, I know gold is not a gemstone, but we value gold. Gold is not a natural occurrence on our planet. Gold is from outer space. We got it from asteroids from outer space.
Thank you for that answer, Victoria. It looks like that's all of the questions. And so I would like to thank you for the excellent presentation and for being with us today.
Glad you enjoyed it. Thank you.